Okay, so I took some notes on the lecture I was speaking about before, which is lecture number 4, MIT 5.11, Principles of Chemical Science. And what I have here, you can see in my notes, they're not so great, but they're okay. Something that really stood out to me, she gave a problem and the whole class gave an answer for it. It's if a beam of light with energy 8.0 electron volts strikes a gold surface, what is the maximum kinetic energy of the ejected electrons? So something she goes on to say in the later minutes of the lecture, she says that the number of ejected electrons from the surface of a metal is proportional to the number of photons absorbed by the metal. Though that seems intuitive, it's not so, especially if it's the first time you've ever done a problem like this. It's really interesting that she actually said that. Not too many people will give you that information. You have to ask for it. And she also goes on to say, because of that reason, let's say you have 6 photons in, you get 6 electrons out, and that's saying that the 6 photons have energy greater than the work function of a particular metal. So she goes on to say that the photons in equals the electrons out, as I just said, and then it goes on to say the intensity of light is proportional to the number of photons emitted. And I think she may have messed up. I think she may have meant electrons emitted. I don't know. So I thought that was a really good example. Something else I wanted to talk about. Let's see if I can find it. Okay, so one really good thing I like about the lectures is it gives you a historical point of view. So she talks about Einstein and him using the speed of light to relate wavelength and let me see, goodness, I can't remember. Sorry, not wavelength, frequency to energy. The equation E equals H mu, which is E equals H C over lambda. C is the speed of light. Let me just see if I can remember what she says. My memory's not so good, so I just have to go back to my notes, and that's why I took so many notes. If you don't know, H is Planck's constant, so she gives the equation E equals hv, and V is actually nu, and V is the frequency, and she says that V, the frequency, equals the speed of light over lambda, which is something you can get from a textbook. But she goes on to explain that Louis de Broglie, I think I'm saying his name wrong, I don't know. So Louis de Broglie comes up with this whole concept of momentum, and you can use momentum to get the velocity of a particular electron that's been ejected, because she says that you can't use the E equals hv equation to figure out the frequency or the speed of an emitted electron or the energy of an emitted electron. So you have to use those two equations that she'd given you in the past, which would just be the momentum equaling, sorry, let me just go back to my notes because I'm speaking from my memory now. Memory's not so good. Let's see. Okay, so she goes into this whole spiel about matter also having its own wavelength, and that we're not able to observe the particular wavelength because it's so small. It would be very hard for the human eye to see it, and it would be very hard to measure it. So she goes on to say that this concept came from Louis de Broglie's dissertation, his senior thesis. And she says that momentum equals mv, which we learned that from physics, and there's also a quantum mechanics equation. But momentum also equals Planck's constant over the wavelength. So if we take these two things and we we set them equal to each other. Sorry, we set them equal to each other. That's mv equals Planck's constant over the wavelength, and from that we can get the velocity of the electron that's been emitted. And I thought that was a really, really good equation. That's something you could just commit to memory. So we have, if we just rearrange the equation, we have lambda equaling Planck's constant over the velocity, and then we just multiply that by the mass. So I'll repeat it. It's just lambda equaling Planck's constant times the mass. Sorry. Let's start over. So it's just lambda equaling Planck's constant over mass times velocity, and we get those from those two equations. And if you forget it, as you probably will your first time using it, you can just derive it again if you remember that momentum equals mass times velocity, and if you just remember momentum of matter that has a wavelength just equals momentum equaling Planck's constant over lambda. Just set those two equations together. It's really important, really easy. It will get you a few points on the MCAT, will get you a few points on a test if you need to. So I hope you found that not too confusing and really interesting, although I'm a science geek, pretty much always have been, but I thought it was interesting, so I hope you like it. Okay, bye. Oh, MIT Lecture 4 5.111.